Yes, I mean, that's okay, yeah. Okay, so I'll talk more about the future, again, starting with La Jolla. Some fundamental study developing this nano machine for future medical, robotic, nanosurgery, drug delivery. So this is our post-lunch menu. We'll talk about why nanomachine, our inspiration from biological motor, how to design powerful machine, how to control their motion, and then we'll discuss biomedical and biosensing applications. So actually, we are all familiar with big machine. These are, again, 10-meter machine, 2-meter machine that use chemical energy to perform different tasks, mechanical operation, this is when I was about 15 years ago, dark era. This is a big machine, 1 meter long with the US Navy down in San Diego. Up in Point Loma, we use this submarine or AUV to detect explosive in San Diego Bay. So we put the sensor here, and this was swimming in the ocean to locate explosive, as you can see in the next video. So we mount the sensor, ONR support, and then we deploy it to look for a plume of explosive. So this is 1 meter long. You can see it swimming in the ocean. And now imagine you take this 1 meter long and you shrink it by 1 million, from 1 meter to 1 micrometer. Now you get also the same shape of a nanowire, but now instead of swimming in the ocean, it can swim in the blood vessel and look for a cancer cell for Professor Zhang combinatorial drugs. So now we can swim in a blood vessel because we shrank it 1 million times. And instead of explosive, we look for disease cell. And again, this is not my story. Already Professor Zhang mentioned this famous movie in 1966. 45 years ago, we were dreaming about sending this nano vehicle down to the blood vessel, locating the disease cell and destroying cell. So why it takes us so long, 45 years, to realize this vision? We have major challenges to swim in the nanoscale, how to power this little nanomachine and how to navigate them to their destination. And this is all about nanomachine, and it's not only for drug delivery or nanosurgery or biopsy, but there are many other applications, nanofabrication, nanoscale assembly, sensing, robotic, and so on. So there are a lot of interest. But again, to realize this vision of swimming at this low scale, what we call low Reynolds number, we have to overcome major challenges because physics work differently in the nanoscale compared to this big swimmer. It uses conventional swimming. This little swimmer, like the nano vehicle, you have to develop a new propulsion or swimming mechanism because you have to overcome the viscosity effect that dominated what we call low Reynolds number and the thermal Brownian noise or motion. So we have to design new swimming strategy for this little swimmer. Strategies that overcome the viscosity effect and also allow you to navigate to your destination, overcome this Brownian thermal noise. Luckily, nature have done a lot of the work for us and developed very smart, sophisticated machine over billions of years of evolution. And this little machine use a biological fuel like ATP, energy-rich molecule, and they perform very advanced function like transporting inside the cell with very good efficiency. These are two examples, the myosin in our muscle and the kinesin in our cell, that they overcome this viscosity effect by moving on this microtubule track or nano highway. So you can see the kinesin carry a big cargo, but he's moving on this nano track that provides this guidance to the destination. You can see again the microtubule and the kinesin. Here is another microtubule, and he carry a large vesicle from one side of the cell to another side of the cell by moving these 8 nanometer steps. And you see how he carried this huge cargo from one side by being guided on this microtubule highway or nanotracks. So this provides us the inspiration and a lot of the knowledge how to develop synthetic nanomachine. We also want to operate on fuel or fuel-free and to do different tasks transporting cargo like this microparticle loaded with the drug, to do it in vivo, in vitro. So nature gives us the inspiration and all the knowledge, and when we develop our man-made machine, we ask ourselves, can we compete with biological motor? Can we, how nature address these challenges? What type of fuel can we use? What type of operation we can perform? And how to combine this little machine with engineering environment like microfluidic devices and so on. So we will discuss today 4 types of nanomachines, some of them based on fuel, in our case peroxide, and some fuel-free for in vivo application. We'll start with the fuel, this nanowire motor. This is bi-segment nanowire that in the presence of hydrogen peroxide, they start to propel autonomously. The platinum gold segment, and they move at 10 micrometer per second. So 10 micrometer per second is about 5 body lengths if you calculate the relative speed in terms of to the body. So it's 5 body lengths. And these are prepared. We can mass produce them in a membrane template which have pores, a million of pores. So we can generate million of these by sequential deposition of this platinum and gold. So we need platinum, gold. We plate the platinum, the gold. Then we dissolve the template, releasing a million of these little swimmers. So this is the platinum gold, and we asked, can we make it stronger and faster? So 3 years ago, we incorporated into the platinum some nanotube, and we got some dramatic improvement, about 4 times improvement in the speed with nanotube and without nanotube. And this is because the nanotube accelerates the reaction of the fuel, this oxidation of the fuel. And it's not, you can see this track instead of 8 to 10, about 40 micrometer per second, so about 20 body lengths per second. So we have a better fuel efficiency, better gas mileage using this nanotube in the platinum, because again, electrochemistry of the peroxide oxidation is much better at the platinum nanotube. So we ask ourselves, can we do even better? We can also modify the fuel. And in addition to modifying, adding the nanotube, we added a little bit of hydrazine, which is a rocket propellant, into the peroxide. And we got the world record that Professor Wang mentioned. If you look at this guy, this is the world's fastest nanomotor. It's go, and this I slow it, you can see it again if you missed it. Up, there it is. I missed it even, yeah. Let's do it again. Here we go, yeah. This is slow motion because it's too fast. 95 micrometer per second. But again, put it in perspective to this guy from Jamaica, Bolt. He's the world's fastest sprinter. He ran the 100 meter at 9.56 seconds. But he's only 5 body lengths per second. He's almost 2 meters long. So it's only 5 body lengths compared to my guy, which is 2 micrometers. He goes 50 body lengths per second. So it's all about relative speed. Yeah, so my guy is much, much faster compared to this in terms of. But we can do better later on. But it's not only the speed. More important, the speed reflects the force and the power. So if you do all the calculation with the nanotube and the hydrazine, we got significant improvement in the power, which is important to carry this cargo that Dr. Zhang will give us later on. And we also improve it even more 2 years ago by replacing the gold with the gold-silver alloy, which is an excellent catalyst for peroxide oxidation. And we got a little improvement. You can see this guy now. So it goes 120 body lengths per second. So it's about 120 micrometer per second. So it's 60 body lengths compared to platinum gold, which is only 10 micrometer per second. So, and we can tailor the speed by tailoring the composition of the alloy. You can go from 25% silver, 50, 75, and the speed increase to above 100 micrometer per second. So we have a lot of speed, force, and power. The second challenge is how to steer and how to navigate this little motor to the destination. So precise motion control is very challenging in the nanoscale. We talk about the Brownian motion. We have to overcome this. So how to do these little motion control toys at the nanoscale? We have different tools that we develop: magnetic control, temperature control, light, chemical stimuli, electrochemical. We will see few of them. Start with the magnetic, where we have putting basically a magnetic segment like nickel into the nanowire, and we can modulate the magnetic field. We can go on and off and can do stop and go by stopping it. You can see we swimming, then we bring the magnet, we stop it, and it's very repetitive. You see 3 cycles, stop and go. We can also use it to turn it like a steering wheel by rotating the direction of the magnetic field. You'll see in the next video, now we will turn the magnet like your steering wheel, and you rotate it like 90 degrees, and now you can see you can control, like in the intersection, you can swim to the right now. You see, we go, we slow down near the intersection, then we turn the steering wheel, we'll go this way to the right turn, yeah? Go. Then you have another stop sign. So we'll see this later on in microchannel and so on. We can go up, a very complex channel, up again. Where is this? Yeah, so you can do UCSD, we can do all these complex patterns that we later on use it for nanofabrication without the tip. So we can functionalize reagent and do patterning like in DPN by having localized reaction, metal reaction, or electropolymerization by having this, again, reagent A on the motor, reagent B in the solution, so you guide it, so only where you predetermined path you get the electropolymerization. Another stimuli is temperature. Temperature can control the electrochemical reactivity and then the speed of the reaction. So again, we can have thermal pulse of temperature, and like starting with room temperature, then we step it to 50 degrees, sudden acceleration, then we slow it down again, and it immediately, unlike the Toyota, we can slow it down. If you don't believe it, you can see again. Room, step, and again we put the brakes, cool again, it stop instant because of the control of the kinetic of the electrochemistry. These are very reproducible. You can see at high temperature, 5 thermal pulses. So it's again fastest kinetic of the electrochemistry. We can also control the fuel concentration by putting electrode to deplete it. So if you deplete, you slow it down, or you can generate more fuel from oxygen, you accelerate it. Another stimuli is chemical stimuli. We observed that silver, a little bit of silver, give acceleration. You can see this video. And this is very selective. So you can see only silver give you this selectivity. Go to 50 micrometer, all the other ion actually slow it down, and we use it to develop biosensor because we use silver nanoparticle as a tag for DNA or protein detection. So we ask if silver is a good accelerator, we can use our silver nanoparticle and use a new type of motion-based bios. Oh, what happened here? Something. Yeah, it's sorry. Yeah. Where we are, go back to our, yeah, so we are here, yeah. So again, we do the DNA hybridization, capture the silver particle, and then put the fuel, and it dissolve the particle, you get acceleration of the nanomotor. So all you need is a microscope, and you get nice speed signal or distance signal, different concentration of the DNA target from femtomole to picomole give you different speed and distance signal. Here you can see a movie for different bacteria concentration. We can detect the RNA. You can see the nanomotor moving at different speed or distance because of the more bacteria, the more more silver you collect, and the faster is the speed. So we have the motion control, we have more force and power. Can we combine it to carry large cargo like this nanoparticle loaded with drug or liposome. So we combine the motion control with the larger force, and you'll see how we can pick a cargo and direct it and transport it. You see, we pick the cargo, we transport it, and then we release it on demand, and then we go and pick another cargo. So this is about 5 micrometer cargo, or actually this is 2 micrometer magnetic bead. We also, with Professor Zhang again, you can see these are either is PLGA particle or liposome loaded with drug. So they have also iron oxide magnetic nanoparticle to allow magnetic pickup on the nickel segment. And we can evaluate different particle size, and you can see the speed will depend upon the size of the particle. As you expect, you'll see the video, the very slow with the big particle, faster with the little one. And this is what you expect from Stokes' law. So the speed will decrease. Again, you can see it again. So 2 micrometer, 1.2, and 0.7 micrometer particle size. So we have all this capability. We have cargo towing, we have motion control capability, we have improved speed and power. Can we use it to develop a microchip device based on autonomous transport? The goal is to have a microchannel network with little channel of 2 to 5 micrometer with different cargo to manipulate within the microchannel in a selective fashion, like this cartoon. The motor with a receptor go and pick one of the selected cargo based on the receptor, transport in a microchannel, drop it on demand and the destination, and go and pick another cargo. So it's all in lab on a chip scenario. For diagnostic application, you'll see cell sorting and so on. So here is example of the same what we have in the vision in the cartoon. Here we have a little nanomotor in the intersection. We can guide it to go this way. We can go different complex pathway within the channel. These are 4 different motors going different predetermined paths. So we can control the transport within this 2 micrometer channel, if you can see this guy. So we have directed motion. Can we combine it with the cargo pickup, cargo manipulation? You'll see in the next videos that the motor go and pick the cargo, and then, like in the cartoon, and manipulate it within the network. You can watch this video going and picking it in the microchannel entrance. We enter the intersection, and then with the cargo decide, like in the cartoon, go this way, carry the cargo, drop the cargo, go and pick another cargo like we have in the cartoon. Now we want to make this car smart without any driver, so we can make their own decision by sensing the surrounding environment. Can we implement this, avoid the driver, and just let them driving without any accident? We want to avoid this collision, to avoid this obstacle, self-smart anti-collision capability into this nano vehicle. One way to avoid this obstacle is to cover it with an enzyme that consumes the fuel. Since we use hydrogen peroxide, we can have a catalase or peroxide that deplete the local fuel, and in this case it will avoid this. Another way is inspired from nature, is this collective or swarming of animals. So we're all familiar with the swarming of honeybees or trail of ants. Can we induce similar collective behavior, coordinated motion of synthetic nano machine outside the nature? Can our synthetic machine communicate with each other to form this self-organized assembly, like the schooling of the fish or flocking of the birds? And how this population of synthetic machine can interact with each other to cause this type of swarming and grouping? So this is the work of this guy that just entered the room. He found that if you put a little hydrazine to this gold nanoparticle, you induce this swarming and grouping. So if you watch his movie, you can see that just spiking the hydrazine Here we spike it, and then after 10 seconds, you start to see this grouping and swarming that get larger and larger. They merge with each other. You get larger grouping, and basically they have chemical reaction, mimicking the secretion of chemical by animals. So you see the small swarm get merged with larger one, and after 20, 30 seconds, you get this type of self-organized assembly, which again mimic the flocking of birds or others. So it's again coordinated cooperative action of this synthetic nanoparticle. So we have all these capabilities that we talk about: motion control, smart device, power, force, and this allows us to do all these biomedical applications. We talk about drug delivery, diagnostic, nanosurgery, biopsy, and this is what we are trying to implement. One challenge is this nanowire do not propel good in biological fluid. Another one is the type of fuel. We need to go to either fuel-free device or to go to green or biological fuel. So the first challenge is we replace the nanowire with microtube rocket. These are propelled efficiently by oxygen bubble mechanism in biological media. So they have an inner surface of platinum generating this oxygen bubble from the fuel, and this causes this propulsion. Here is another one that we developed recently with, you see the platinum inner surface and conducting polymer, and then you can see the way we prepare him in the template. And then you can see the movie, how fast they are moving. You see in the bubble, and these are extremely fast again, 200 body lengths per second. These are only 5 micrometer long or 8 micrometer long. So it's extremely fast, few hundred body lengths per second. And we guide them with a nickel layer that we incorporate inside this body. And we can mass produce them. You can see them in a template depositions. A lot of material research, fundamental, how to make this bilayer tube of polymer and inner surface of platinum. And then we use them to isolate biological media. We functionalize them with a receptor selective to cancer cell or DNA or protein. And here are some receptors for, again, for protein, for cell, for nucleic acid, and they will move in the blood. This is again work with collaboration with Professor Zhang. We put the anti-pancreatic cell antibodies that will go in the blood and collect this pancreatic cancer cell. So this is the concept. Again, you can have selectivity against normal cell. We control the surface chemistry to minimize non-specific absorption. And we see that this coating does not affect the propulsion in blood. We can swim. You see the bubble of oxygen with the surface coating. And then this slide will show you the pickup of the cancer cell in a buffer and in a serum. You can see the cancer cell transported by the rocket. This is now in the blood. It's more slow because of the viscosity. Then we did the same nucleic acid isolation. We put single-stranded probe, and this will go on-the-fly hybridization and isolate target DNA or target RNA, bacteria detection. You can see this E. coli detection. We use fluorescence to, with a sandwich assay, like you see here, we have a fluorescence bead to visualize the hybridization, so you can see the control without the fluorescence, and here is the target E. coli, and you can see the video. A lot of the fluorescence particle and none of them in the control. And this is excess of the control. And this can operate in urine, saliva, in blood, and so on. And the goal is eventually to have a lab-on-a-chip that will do this diagnostic without any pumping or without any high-voltage electrophoretic. Just have the nano machine go to the blood, pick selectively the target analyte, can enrich it, isolate it, tag it, and then do the detection in a microfluidic channel. So this was about in vitro. For in vivo application, we'll need to develop fuel-free unless we can operate with glucose or ATP. At the moment, we cannot operate on glucose, so why not to use fuel-free? We developed before some electrically propelled diode nanowire, and now we're working on magnetic nanoswimmer. These are inspired from the E. coli flagella that rotate and propel the flagella. So we develop artificial flagella based on flexible nanowire that you can see this rotating, with rotating magnetic field. Now it's stopping the magnetic field, take some rest, resume it, and go again. So this is a flexible nanowire with a flexible joint that allow you to propel by magnetic, mechanical deformation of the joint. So we have a flexible joint, either a silver, or now we work on some polymer one, when we have a nickel head that give the magnetic rotation. So it also operates in blood and serum. You can see this guy swimming. Actually, this is only bisegment. It's only nickel and polymer, or nickel and silver. We eliminated the gold. So we can do it without the gold, just nickel and silver or nickel and polymer, and you get this bisegment swim extremely fast, again, about 10, 20 body lengths per second in the blood. And eventually we are dreaming about some nanosurgery that this little guy will go and clean our clothing after this big lunch. Or we also develop a hybrid machine that combines this magnetic fuel-free propulsion with fuel operation. So just by putting a little bit of platinum, you can also get it fuel-driven. So you can have both the platinum gold for catalytic propulsion and this part for the magnetic fuel-free. So we have our hybrid Volkswagen, can go either way, catalytic or magnetic. If you run out of fuel, you can start your magnetic, as you can see here. So here is the same swimmer with the fuel or without the fuel. Here we have, with the fuel, there is no magnetic, but if you run out of the fuel, you can apply your magnetic, and these are some control. So in conclusion, again, we developed different type of nanomotor, added a lot of new capability and sophistication to do a wide range of biomedical application, biosensing application, with the future is all up to our imagination. Again, thank the people who did the work. Here is Daniel, 7 other people, funding, and thank you all for your attention. Thank you very much.
Thank you very much, Professor Wang. Do we have any questions? We have a little time. Okay, first one.
I have a question about, you said that you're going to insert these nanomotors into your bloodstream, and how would you get rid of it? Because they're in your bloodstream, and I'm not sure if you mentioned this, but are they biodegradable? Do they degrade in the body, or is it going to be, how do you get rid of them, taking out the body?
First of all, we are working to make them biocompatible. We have to get rid of the silver and all the nickel. So the moment we make them biocompatible, at least, so we use different polymer like chitosan or other polymer that will not have toxic effect. But eventually, if they can self-degrade it or can be removable, yeah. But it's still a long way to go for the in vivo.
Great question. Do you have another question for Professor Wang? Not going to force it then. Oh, there we go.
One more, yeah.
I had a question about if you could go into further detail for catalytic propulsion and magnetic propulsion. Does one drive the other, or?
In which one? In the hybrid case or in which?
Yes, yes.
No, in the hybrid we have two options, like a hybrid car. You can drive it with the fuel or electrically in your car. In my case, if I have the fuel, it will propel catalytically. If you run out of fuel, you can start the rotating magnetic. So it just gives you the option. It's adaptive vehicle that can switch operation like your hybrid car, yeah.
Well, with that, I want to say thank you so
Thank
much
you.
for
Thank
taking
you.
time and being here.
No worries, yes, everything.
Wonderful.